Okay, covalent bonding. We already looked at ionic, and I just want to real briefly talk about the conceptual difference between ionic and covalent bonding. Ionic versus covalent bonding. In ionic bonding, we're looking at something like this, a model. The conceptual model is that we've got two ions sticking together. That's an ionic bond. And actually, I shouldn't really say two, because it's usually many. Right? So in other words, this could go on and on and on, and it typically would just form a crystal like that. Ions sticking together, but the point is the whole atom is charged. And it's either negatively charged or positively charged, and then they stick together. Whereas with covalent bonding, we have a different model. We have two atoms attracted to the same electrons. Two atoms attracted to the same electrons. Pair of electrons, we might go further and say pair of electrons. It happens in pairs. It could be one pair, two pair, three pairs. That's a single, double, triple bond. But those are, it's just two different models, okay? And what you're going to find out as we go through this is we're going to find out that the line between these is not well defined, actually. So there's they actually lie on a continuum, and we'll get into that later today. So we want to focus on covalent bonding here and go into a little more depth as far as what's happening. And I want to start by just drawing a picture, and I'm going to show this right here. This diagram is actually supposed to be H2, so that's why there's only one positive charge here and one here, because these are supposed to be hydrogen atoms that just have a single proton. But let's look at F2 to make it a little clearer maybe what's going on. So in fluorine we have a nucleus that has a 9+ charge. That's a 9, not a G. We'll have 2 electrons in the 1s sublevel. So this is the 1s, and then we'll have, this is the 2s, 2p5. There are going to be 7 electrons in here. So that's one fluorine atom. Now the fluorine atom is going to bond in a covalent bond. It can bond with another fluorine atom. Whoops. Like this. Whoops. Sorry. Now let me just I'm going to make these electrons in here a different color. Just like that. So now what's actually happening here is there's an overlap in the outer shells of these two atoms. The atoms are sharing, they're each contributing 1 electron to this bond, okay? So this right here is the covalent bond. Now think about what that word means, covalence. Co is the sharing part, like cooperation. So that's the sharing. And then what is valent? That's standing for valence electrons. So they are sharing valence electrons. Notice that they each contributed 1. Now this is not always the case. Sometimes one atom will contribute both of the bonding electrons, but in many cases they each contribute 1. And then they are held together because the 2 nuclei are both attracted to those electrons. So I guess I could try to draw this in here. There's going to be an attraction to both of those nuclei from those electrons that they're sharing. It's as if those two electrons are part of both atoms' outer shells. The atoms feel like those electrons are theirs, both atoms. And so that's what holds them together. So they are held together by the mutual attraction to the same electrons. The atoms are held together by mutual attraction to the same electrons. Just like if you had two people, all right, and let's say these two people were both attracted to the same game controller, all right? And so they are held together because this is the, what does that look like? That's a game controller. So it's like a Xbox controller or something. So because they're both attracted to the same game controller and neither of them is going to yield, they are going to be a unit until one of them gives it up. Right? That's the idea. So they become a unit because they're attracted to the same thing. In this case, of course, that would be the electrons, and these would be the two atoms. Now, why do they do this? So why do atoms do this? Any ideas? Why not just be content with what you have? Yes? They want a full outer shell. Okay, so let's write that down. They want a full outer shell. That's good. And so let's look at that in a little bit more detail. Let's say we've got our fluorines again. So here's fluorine 1s2, 2s2, 2p5. And here's another fluorine 1s2, 2s2, 2p5. They don't have a full outer shell just like that. But here's what happens if they get together. They both become, if it's F2, or in F2, they both become like this. How does that work? Well, let's look at it. You know what? Let's look at it with an orbital filling diagram. So here's fluorine. It's 2p. Right now, it's got a gap. Here's another fluorine over here. And what we'll do is we'll show it like this. See that? This then is the covalent bond. And it actually is an orbital. What happens is a new orbital forms called a bonding orbital. And it kind of takes the place of that half-filled orbital that was on each atom. And so in so doing, they both become like this. Now they're kind of cheating because there really aren't a total of 20 electrons. There's only 18. And yet, with only 18 electrons, by sharing, they're able to make it like as if they both had 10. So by sharing, they both achieve noble gas configuration. In this case, they're like neon. Neon is 1s2, 2s2, 2p6, which is very stable. That's the way we usually say it, right? We say this is a very stable configuration, so this is why it happens. They do it to get a full outer shell. But what about larger atoms? And we're talking about n equals 3 plus here. So when they have a higher sublevel a higher principal energy level than 2, what happens? Remember that principal energy level 3 can hold 18 electrons. So let's look at chlorine. Cl2 is the molecular form of chlorine. Now, one single chlorine atom is 1s2, 2s2, 2p6, 3s2, 3p6, 3p5, sorry. But in Cl2, it is like argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. Because it gains, what it does is it shares one of its electrons, and so it gets to have the benefit of an electron of another chlorine atom. So that's when it's, yeah, sorry, that's 3s2. Now, in this case, we can't really say the outer shell is full. The outer shell, in this case, is not full in an absolute sense. Why? Because the third energy level also has a D sublevel. And the D is not filled. Follow me? In fact, it only has 8 electrons in this case. But it's as full as it's going to be, while it's still the outermost level. It's as full as it can be while still being the outermost level. In other words, what happens if you tried to add another electron to that thing? It wouldn't go into the 3D. It would go into the 4s1. Okay? And let me just write a note over here. Adding another electron, one more electron, opens up n equals 4. Okay? So you can't have more than 8 in the third energy level while the third is still the outermost. As soon as you try to add another electron to that atom, you open up level 4, which is now the outermost level. And that's how it happens. As you go down the periodic table, same thing. Just when you think you're going to get more than 8 electrons on the outside of the atom, you open up a new outside. Just when you think you're about to get more than 8 electrons on the outside shell of the atom, it's not the outside shell anymore. There's a new one that's empty. Okay? So that's why you get this pattern of 8, 8, 8, 8 that the early chemists saw. Because of that. And what do we call this 8? We call this an octet, or sometimes a stable octet. And another way of saying what we said up here, they want a full outer shell, we can now say a little bit more precisely, they want a stable octet, okay? Where they want 8 electrons in their outermost shell. So that's one way of saying it. Are there questions about that? explanation? How that works. This right here, how we get a noble gas configuration. By the way, the same thing happens when they're forming ions, right? Chlorine could do the same thing by becoming Cl minus. It could gain an electron and it could achieve the same goal. So it's the same explanation for why they form ions. Let me just make a note of that. This is the same explanation for why they form ions. All right, but I want to go a little bit deeper, if there aren't any questions. Because this is okay, but the fact is that atoms don't think and they don't have desires. So they don't think about, boy, I'd really love to be a noble gas. They do not do that, so what are they really doing? So let's go down to try to get kind of a mechanistic interpretation. Can we explain this in terms of forces? And the answer is yes. Let's look again at our example of fluorine. There's 2 electrons in here, and then there are 7 out here. So the effective nuclear charge is equal to 7. And remember what that tells us? That tells us about the force acting on these electrons right here. In other words, this electron experiences a force from the nucleus equivalent to a nucleus with a +7 charge. Now, I didn't state that real well, but the idea is this guy he is repelled by 2 negatives. He is attracted by 9+. He's being repelled by these, all right, but he's being attracted by the 9 inside. And so it's as if he's being attracted by 7, but that's very strong. Actually, fluorine has the highest electronegativity of any element. So those outer electrons are really strongly pulled. So that's part of our explanation. So that's step 1. Step 2 says there is still, so we can say, and there is still room in the outer shell. So in other words, there's a really strong attraction for electrons. This atom has a really strong attraction, and there's still room for it to suck an electron into the outer shell. So that's what it does. So another atom comes along, and it'll suck an electron in there. It'll either become an ion, or it'll form a covalent bond. So let's say another fluorine atom comes along. Here we are. Here's our first electron. I'm just going to draw the same thing I drew last time with our 2 shared electrons. Okay, that's what happens. So they both have a really strong pull on electrons, and there's more room in their outer shells. So what do? They're going to add electrons to themselves. Now, let's say instead of a fluorine atom, what if this one right here, instead of fluorine, was sodium? Same thing would happen, except that fluorine is so much stronger than sodium that it would rip that electron right away from the sodium atom and form an ion. But in the case of fluorine, fluorine versus fluorine, they both have equal strength. So one cannot steal it from the other. Instead, they fight over it forever. And it's an equal fight. Exactly equal in this case. So they are bonded together by their equal attraction for those two electrons and their strong attraction. Now here's a question though. So to kind of finish this, we could say step 3. Step 3, once the bond is formed, or we could say once an ion is formed, once the bond is formed, there is no further, there is no more room for additional electrons. So even though these atoms still have a very strong attraction for their outer shell electrons, they're not going to have a tendency to form more bonds because there's no more room in that outer shell. So here I am, I'm an electron looking for a place in this world. So I come over here and I'm like, and they're like, there's no room. Okay? So because the shell's full now, watch, if let's say I just was able to kind of hang out right on the edge, on the periphery, right? And just kind of creep around there. Here's the thing. There would be no attraction of that atom for me. Why? Look at this. I'm going to be repelled by 9. This guy out here, so if I'm floating around on the outside, I would be repelled by, actually not 9, by 10 electrons in the outer shell. Because look at, count them all up. Now there's 10 because he's sharing this one, right? I'd be repelled by 10 and only attracted by 9 plus. In other words, I'd bounce right off. See what happens? So there's a big difference now. And so that's one way to explain covalent bonding is in terms of electronegativity and effective nuclear charge and the electrical forces. And by the way, we could use the same explanation to explain the formation of ions. It works the same way, which is a hint that there's not so big a difference between ionic and covalent bonding as we make it seem. It turns out there's a continuous range from covalent to ionic. It has to do with how equal the sharing is. Okay, third way of looking at it. In terms of potential energy. In terms of potential energy. Now, potential energy, some of you may not be real familiar with that term, so let's look at a real basic case. If this is a hill, okay, and this is a boulder, right now, this position right here is a position of high potential energy. And if the boulder were down at the bottom, that's a position of low potential energy. And here's the thing. In the universe, systems or things tend to move from high potential energy to low potential energy. And by the way, when they do that, that energy is not lost, it's converted, right? It's usually converted into, say, kinetic energy. You might remember that this is the same way it works for an electron, right? The electron is doing the same thing in the atom when it falls from one level to another. It's going from a high to a low potential energy. So we can explain bonding in this way too. Bonding works the same way, but it's not gravitational potential energy. It's electrical potential energy. electrical potential energy. Now, the best way I can describe this is with magnets. So magnets are not electrical, they're not using electrical potential energy, but magnetic. The thing is, electricity and magnetism work very similar. For example, magnetism can be repulsive or attractive, just like electrical forces, whereas gravity is always attractive. So right now I have these so they're north to north, so they're repelling each other. If I push them together, because they're repulsive, if I push them together, this is a high potential energy situation. This is low. How do I know? Because if I put them like this and then I let them go, they will move to a lower potential energy just naturally. So I can add potential energy to the system like this. So basically this is storing energy right now. And if I let it go, it will naturally move to a lower potential energy position. If I move them so they're attracted to each other, now it's just the opposite. Now if they're separate, they have high potential energy, and they will naturally move to a lower potential energy position. Now what happens to the potential energy? Let's move them so they're repulsive again. As they move closer, the potential energy goes up. It's higher. In other words, potential energy of this system is higher than this system. So watch. If I put this thing on the ground, and I just have it like this, and I let it go, it has a little bit of potential energy. But if I push them right down next to each other and let it go, it has a lot more potential energy. Two atoms. Let's make a graph. And on this graph, we're going to put potential energy on this axis, increasing. And on the y-axis, we're going to put distance, x-axis, we're going to put distance between nuclei. And what we're going to do is we're going to make this graph for H2. So we're going to make an H2 molecule here. So what we have are two hydrogen atoms. So over down at this end to the right, we have two separate hydrogen atoms. They're separate. Two separate hydrogen atoms. Over here at 0, at the origin, we have two atoms that are so close that their nuclei are actually touching. In other words, this is helium. Okay? So that would be fusion, folks. So at 0, the two hydrogen nuclei have actually touched each other. Now what would happen as I go from, I'm going to start out here, and I'm going to go this way. So as I move from right to left, one thing that's going to happen is they're going to start to repel each other. The first thing that's going to happen is the outer electrons are going to start to repel each other because they first come into contact. And they're going to be repulsive, so that force is going to be repulsive, so it's going to look like this, my potential energy curve. Just like when my magnets are repelling each other, if the force is repulsive, then the closer they get, the more potential energy I have. Okay? Now let's label this. This we'll call electron to electron repulsion. Electron to electron repulsion. Now, if I got even closer, the other thing that's going to happen as I get closer is I'm going to start to have interaction between the nuclei. They're going to start to repel each other. Because remember, they're both positively charged. So let's draw that in here. We'll draw it a little bit further to the left because they'll start interacting after the outer electrons. This is going to be proton to proton repulsion. all there were repulsive forces, the bond would not form. So there must be some attractive force. That is between the outer electrons of one atom and the proton of the other. So this would be attractive. Let me use a different color here. And that is going to look it's going to look like this. In other words, now if it's attractive, it's like two magnets attracting each other. We say the lowest potential energy is when they're together, and then it gets greater as they go apart. So this one here is going to be electron to proton attraction. All right, now if we added these up, we would get something very roughly like this. It wouldn't be just like this, in fact, it would be changed because we'd be adding the curves. But you get the idea. You get that general shape. Now, how do we use this? This is a potential energy curve, and you'll see these as you move on in physics and stuff. We start with the principle that systems, things tend to move to the lowest potential energy. So look at our x-axis. That's the distance between the nuclei. What this is telling us is if our system starts out here at this distance, it's going to move until it's at the low point, which is something like that, where the atoms have merged their electron clouds, but the nuclei are not touching. So it's going to move to some middle point, which is the minimum potential energy. And I have a little illustration of this. It's a model because, again, potential energy basically works the same with gravitational potential energy as it does for electrical potential energy. So
you've lost your marbles.
Just one. Okay. So let's say these are my two atoms, and I'm going to start with them separate from each other. Instead of in this case, I have a gravitational energy field. And they're going to move to the lowest gravitational potential, which is closer to the Earth. High gravitational potential energy, low, high, low. So if I drop them, they're just going to move until they have minimized their potential energy. It's the same with this. If I had two separate hydrogen atoms, they were not in H2, they're just two separate hydrogen atoms. If they come close enough to interact, they will automatically bond together like that. Just like these marbles, and for the same reason. For the same reason that those marbles are right now touching each other. These two will form a bond. It's potential energy. They're just going to where there's the lowest potential energy. Another way of saying this is there's a balance of the attractive and repulsive forces. At this point right here, the attractive force equals the repulsive force. Well, not exactly. So these two will move around, and in fact, it might even be just like that. They might kind of bounce off. They might dance around each other for a while, bounce off of each other, but eventually they're going to settle into that minimum potential energy position. So if I just redraw the graph just so that it's clear what it would look like. In reality, it gets a little bit more complex as we're actually trying to draw this, because for one thing, if there's an infinite separation between the two hydrogen atoms, there's no potential energy. So what we do is we call that zero when they're far apart. I mean, think about it. If one hydrogen atom is right here and another one is in the Andromeda galaxy, there's no potential energy to that system. What that does, though, is it means we can have negative potential energy, but that's okay. What if I dug a big hole in the Earth and we said, if we said that the ground level was 0 potential energy, and then we dug a hole in the earth, we would have negative potential energy, right? Same idea. So this is what it would look like. And basically, this right here would be the bond length. That's what's going to tell you how long the bond is. What's the distance between the nuclei? That's what that's going to tell you. Now, here's the cool thing, that chemistry is really just atoms moving to their lowest potential energy positions. Moving to minimize their potential energies. Chemical reaction, that's what a chemical reaction is. It's just atoms rearranging to minimize the potential energy. Let's say that this was F2 right here. If this is F2, those are 2 fluorine atoms. It turns out F2 is still highly reactive. It's more stable than lonely fluorine atoms, but not than fluorine bonded with, say, sodium. So let's say this is a sodium atom. It comes over here. What happens? As the sodium atom approaches, the potential energy that's possible between fluorine and sodium is much lower than the 2 fluorines. So our landscape changes like this. And suddenly, if they have the opportunity, they'll move to a lower spot yet, which is with sodium. So what's the lowest potential energy is kind of a local thing. It depends on the local circumstances. And atoms are always moving around to wherever the lowest point is in their immediate vicinity. The whole universe can be thought of like that. Just a bunch of atoms looking for the lowest potential energy available. Why don't they look for the highest one? Why don't they go to the highest one? In other words, why the lowest? Josh?
They're at the most stable possible state.
Okay, it is more stable, so if I have, but that's really because it's the lowest. If I had a rock at the top of the hill, this would not be stable, right? This would be stable because it's not going to go up to the top. But why the lowest? Why down? The simple answer, go ahead, Jordan. Okay, it's easier to get there. In fact, you're right, it's easier to get there. In fact, they can't do the opposite without an input of energy. So conservation of energy says that's all they can do is go down. It's just like with an electron. Why doesn't an electron spontaneously jump up in energy level? The reason is that would violate conservation of energy. It can't without adding energy. However, it can go down because it can give off energy. So that's one way to look at it. All right. Questions on those explanations? By the way, the carbon atoms in your body are not in their lowest potential energy positions. The carbon atoms in your body would be much happier as CO2. And they're trying to get there all the time. And it's a constant struggle for you, for your body, to keep them in this kind of a form and keep them from going to this. So that's why you need a constant input of energy. You need a constant input of energy to keep those carbon atoms at a higher potential energy state and not let them all go down and become like this, you know, ashes to ashes, dust to dust, that sort of thing. So, and the whole universe is the same way, really, except the universe presumably doesn't have an input of energy from the outside, so it's a one-way road for the universe. Downhill. Any other encouraging thoughts. It's all downhill for the universe, folks. Unless there's something we don't know, like other universes that could put energy in or something like that, which is possible. All right. Before we finish today, first I want to remind you, you do have a homework video on Lewis structures. And it is just, like I said, I think it's just literally a single video. It's like 8 minutes long. But we've got a few more minutes, so don't stop. Don't put your stuff away. Just write down this homework assignment. We got about 5 minutes, and that's just enough time for me to tell you how to name covalent compounds. The reason is, that's not the way we name them. Name covalent compounds. Actually, sometimes they do have common names, like water, for example, right? But usually that's because the common names go back longer than this formal system. Step 1. Now, the thing is, with naming covalent compounds, the system is different than for ionic compounds. So, step 1 is it covalent? Is it covalently bonded? That is your first question. Do not skip this. And unfortunately, lots of people do. And you just start randomly trying to apply a naming system, and you can't do that. So you have to know if it's covalent. Here's the way to find out. So that's our question. Our answer is, if there is a metal. Don't overthink this. This is very simple. If there is a metal in the compound, it is ionic. Otherwise, it's covalent. So if there's a metal, like iron, or sodium, or lead, or tin, or whatever, I don't care how many hundreds of thousands of nonmetals are on here, it is ionic. As long as there is a single metal atom. Okay? Now, so all you have to be able to do is figure out if it's a metal. And to do that, you look at the periodic table, right? You start right here between boron and aluminum, and you make a little stairway down like this. These are nonmetals, these are metals. Okay? So you have to be able to do that in order to do these problems, because you've got to identify whether it's a metal or a non-metal. Second step. If covalent, so if it is a covalently bonded compound, it's very similar to, well, it's not very similar. It's kind of similar to ionic naming. What you do is you use, there's the big differences right here. You use Greek prefixes to tell the number of atoms of each element. And you might remember that, to your frustration, the method for ionic compounds did not tell you how many atoms there were of each. Do you remember that? It doesn't tell you. It tells you the charge sometimes, but you have to figure out how many atoms there are. Not so with this, so this is actually easier. It's going to tell you the number of atoms. And, secondly, it also, like ionic naming, uses the IDE suffix on the last element. It uses the IDE suffix on the last element. So let's just try one. P2O5. Well, first of all, what I should do is just give you a look at what the prefixes are. So number, you guys are familiar with these probably from geometry. 2, 3, 4, 5, 6, 7. We'll go up to 10, even though you'll rarely need that high. You rarely need beyond like 6. It's mono, di, tri, tetra for 4. Tetra. 5 is penta, as in pentagon. 6 is hexa, as in hexagon. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. So something like P2O5 would be diphosphorus. So what we do is we say the first full name of the first element, just like we do when we're naming ionic compounds. You say the full name of the first element, but this time you do use the prefix di. Diphosphorus pentaoxide. So notice, again, we're using the IDE just like we do when we have monatomic anions on the ionic compounds, like sulfide, oxide, phosphide, and so on. We use the full name here, so the full name of the first element, which, by the way, is the least electronegative. So the one with the lowest electronegativity, so in other words, if it's further left on the periodic table, it will go first. Further left or further down. And then we use the suffix IDE, and then we use these letters, these prefixes to tell the numbers of each thing. So you see how this is much simpler. The only thing you got to do is you got to know, once you know how to use the Greek prefixes, you know how to slap IDE on the end of the word. You don't have to figure out charges. You don't have to figure out charge balance. You don't have to figure out anything, actually. It basically tells you exactly what to write. Diphosphorus, P2. Pentaoxide, O5. Okay? The trickiest part to this is when I give you a worksheet now, it's going to have both ionic and covalent compounds on it. And so you have to make sure that you do nothing before step 1. That's always your first step. Is there a metal in that compound? If there is, then you go one way. If there's not, then you go the other way. Yep. And we'll do some practice. I've got a nice practice worksheet for you tomorrow. Tonight, if you would, take a look at the Brightstorm video on Lewis structures. Let me just give you a word of caution. Some of you have done Lewis dot diagrams in middle school. Here's what I'm talking about. Okay? If you have, just realize we are using a different method, and you have to use our method. So if you start watching the video and you're like, oh, I know how to do this, erase that from your mind. You don't know how to do it the way that we're doing it. Okay? So watch carefully, even if you think you know how to do it. And the reason we're using a different method is we need to be able to do this for more complicated compounds, and for that, the old method does not work. All right, have a good day.